Good evening, ladies and gentlemen. It's nice to see so many people along tonight and joining our discussion here at RMetS. Just as a way of introduction, my name is Gary Johnston. I'm the Scottish VP and chairing the meeting tonight. Just before we start, I would just like to remind you all that this is a talk that has been organised by the METSOC. And it is a charity and a voluntary organisation, and I would ask that you people do consider joining. It's a very worthwhile organisation, and it's something that has got a pedigree, has got a history, and is very worthwhile. So I would encourage you to join. Now, as I said, it's nice to see you all here tonight, and I'm very glad to introduce tonight the Professor, Emeritus Professor of Engineering and Design at the University of Edinburgh. Now, Stephen has asked me not to go into a lot of bio information about him tonight. He's obviously a very modest person, but I must say, if you've read his bio, it is very impressive, and you would almost say it's a superhero CV that he's got here. To go from an apprenticeship in aircraft industry as a fitter and toolmaker, right through everything to design of a seagoing hardware for the Latham proposal for a review of global warming and making clouds whiter. That is a very, very impressive CV. When I was growing up, I knew about the Black Knight rocket, and to be involved in the design of that, of our hovercraft, very, very impressive. So Stephen is going to talk to us tonight about marine cloud brightening as an emergency brake on climate disaster. So welcome, Stephen, and over to you. There will be a chance at the end to answer, for Stephen to answer any questions, so please use the whiteboard on the right-hand side. Thank you, Stephen.
Right, okay. Can I get my slides? I've only got 5 from you yet. Right. I haven't got a thing to click slides. There we are. It's come up. Good. This is a rather amusing double-page spread from Time magazine of 1962, where an oil company is very proud that they are able to melt 7 million tons of ice every day. Okay. They're called the Humble Oil Company, so maybe that was a bit of a mistake. They have changed their name since then. The world ice loss rate is actually 1,000 times higher than that. So 3 orders of magnitude of humbleness. And I want to show you a number of slides which I hope will frighten you. And this is showing the temperature anomaly, and we're 5 degrees higher than we used to be in quite a lot of the north. Here is a very nice way to show the problem. It's by Lee Robinson, and it's a time sequence starting from 1979, going clockwise around up to the present year. The radial distance from the center of that circle is the volume of ice in 10 to whatever cubic kilometers, a big number. And the seasons are going with different colors. So we have the maximum amount of ice in March and April and the minimum in September. And the worry is that we have no ice to reflect sunlight out in the next spring. So let's go to the next one. And here is a map of the Arctic. The Laptev Sea is in the middle of Siberia. And this is showing you the extent of ice through the year. And the worry is that next April, the red is going down. Well, there's a lot of empty water, and empty water is taking in all the sunshine. Let's go to the next one. And this is a top of Greenland, and you can see as the snow melts, it's leaving behind all the soot and dust and mess, which is very good at absorbing the solar energy coming in. Here's another one showing it's rather a difficult terrain for working. If you fall into any of those melt ponds, without wearing special clothing, you'll be dead in a few minutes. This is the Keeling curve. Charles Keeling measured carbon dioxide in the atmosphere, and I plotted it against the different dates of conferences. And so this curve allows you to see how well our dear leaders are getting rid of the problem of carbon dioxide in the atmosphere. And next one, here we are. This is another dangerous thing happening in the Arctic, which is release of methane. This is methane over a long period, and then you get these sudden bursts for a short time. Methane is a lot worse than carbon dioxide. The IPCC said it was 28 times worse, but it's only true if you average it over 100 years. In the first few years of release, it's a lot worse. Maybe these are different assumptions of half-lives, but it could be 200 times worse than CO2 in the first year that it's emitted. This is what happens if you have methane coming up under ice, collecting. If you jab a hole in the ice and set fire to it, you get that great big spread of flame. So we have a really worrying problem. I hope that did frighten you. I hope it frightened you more than it's frightening our political leaders. Now, the solution to this might come from a work by this chap called John Twomey. He's an Irish chap. He did a lot of work on cloud. He flew over clouds and scooped up samples of the drops, and he measured the light coming down from above and the light being reflected back up. And he did a lot of work on the reflectivity of clouds, and he really started the whole of this. And he found that the reflectivity of a cloud, sometimes they call it albedo, depends on the size distribution of the drops. And if you have a large number of small drops, you get a white cloud, and if you have the same amount of water in bigger drops but a smaller number, then you get a dark cloud. And everybody knows that already if they've ever heard the expression, the dark storm clouds are gathering. So that's Twomey. And here is a lovely pocket demonstration of the Twomey effect. The two jars, this is the one on the left has got 4mm glass balls in, and the one on the right has got 40 microns. So there's a 100-to-1 difference in the size of the balls. And you can see that the one on the left has a reflectivity of about 0.6, and this one's up to about 0.9. So you have a pocket demonstration of the optics. And this optics works exactly the same way with little drops of water. And the next person who made a major contribution to this is John Latham. And he knew about the Twomey effect, and he knew that you can't make a cloud drop just because the relative humidity is up to 100%. You have to be a little bit over 100%, but you also have to have a little seed, they call it a condensation nucleus, for the drop to start growing on. Every cloud drop has a little seed in the middle of it. And he was able to work out whether you could spray seawater into the bottom of the boundary layer of the atmosphere, where turbulence would mix it around, and the salt residue left behind when the drop evaporated would be an ideal condensation nucleus. And he worked out how much water you'd have to spray of the right size, and he was amazed at how little you needed to spray to make a big contribution to the cooling. The reason for this is that the air over the sea is very much cleaner than the air over land. And when you boil a kettle over land, there's 1,000 condensation nuclei in every cubic centimeter, but over the sea there may be only 10 to 100. That's why it works at sea and why it wouldn't work over the land. And he found that about 10 cubic meters of water around the whole world would correct the thermal problem since pre-industrial times. And it's all because of these condensation nuclei. Now, his view is not shared universally, and this is one of the chaps who's disagreeing. he was a professor at Chicago, and he said that rather forcefully that this is not a good idea, and perhaps because of that, he was given a chair of physics at what was supposed to be one of the better English universities. And now let's come down and look at the business about the different sizes. This is due to work by a chap called Kohler, and he worked out what size of condensation nucleus you need to get the drop growth. And the size that we want the size of drop we want to make to begin with is 0.8 of a micron diameter, and that is a salt quantity of about 10 to the minus 14 grams. And if you put that weight of salt in, it will collect water and grow from the atmosphere. And it only has to get a tiny little bit over 100%. But if you put in a much smaller thing, this one down the blue curve, that's 2 times 10 to the minus 17 of a gram of sodium chloride. And it has to get up to this humidity before it can get over the hump. And then once it's over the hump here, at the very peak of the blue curve, it can then slide down to the right and grow. And this is going to be a very important choice about the design of this project. Twomey produced a lot of quite complicated results, and to understand them, it's probably better to go to paper by Schwartz and Slingo, and they produced the algebra for Twomey's results. And this is telling you the albedo that you get for a different depth of cloud, a liquid water content, and the number of condensation nuclei in a cubic centimeter. And this is distillation of Twomey by Schwartz and Slingo. This is another way that engineers will need to, it's the same algebra, but this is telling you how many nuclei you need to get a required reflectivity, a required albedo. And that's just rearranging the Schwartz and Slingo. Now, we now come down to some bit of physics, and this is an amazing photograph taken in 1878 by Lord Rayleigh. If you think what photographic technology was available to him, this is really quite staggering. And what he's got is a jet of water coming in here, nice and parallel. It's beginning, move to the right, it's beginning to grow some bulges, and the bulges are getting more extreme, and then they're breaking up into little drops. And this is, we think, the best, most efficient way to make drops. And we were able to design ways of getting a silicon wafer, like for making microchips, putting it down on a grid of holes. These would be holes 5 millimeters diameter on a 7 millimeter hexagonal pitch, and pumping water through them and getting the Rayleigh drops. And there was a lovely software package called COMSOL Multiphysics, and Andreas Siamis worked out all the simulation of Rayleigh's, and it tells you the nozzle diameter you want, and the pressure that you need, and the frequency of the drops coming out, and how much power you're going to be using for different sizes of drops. And we were a bit surprised to see how big a pressure you want, but this is going to be the basic design. And this is one of the things that led us to choose 0.8 of a micron. Now, the next thing you need to know is about the sizes of aerosol in the atmosphere. And if engineers were in charge, we'd have a fairly smooth, monotonic arrangement of drop sizes, but nature doesn't believe that. And there are actually 3 different modes, they call them modes of sizes, size distributions. The very smallest, it's called the Aitken mode, after the chap who made an instrument that could measure them. Then they have the accumulation mode, and that is the middle one, and then there's a coarse mode, which if you're just counting them wouldn't be able to show up on this slide. If you were measuring the weights of them, then you'd see this mode here. And what we want to do is to produce a concentrated stream of drops at about 0.8 micron here, and these will produce, if they've evaporated completely to dry state, you produce, we hope, a narrow spread down around about 200 nanometers, 0.2 of a micron. And one of the reasons we think this is important depends on some work by people in Norway who found that if you spray in the Aitken mode, this yellow thing, this yellow highlighted thing, that it works in the wrong direction. We actually get quite a lot of warming, about twice as much warming as we would get if we were trying to do it in the right size. And this is reinforced by some work by a chap called Greenfield, who was worried about nuclear weapons and fallout. And there's a gap named after him, which is showing how efficient the coalescence and the scavenging of the drops are. And if you look, there's a log scale here, which means there's a tremendously high attrition rate for things in this size and also in the coarse mode. But here we've got a low attrition rate, and our liquid here would be this line here, and as it partly evaporated, we'd be getting a rather salty drop here. If it dried out completely, it probably won't ever go completely dry. It'll probably be somewhere in this range, and this is a very neat fit. I've now got some plots of the equations of the Twomey effect. This set of curves is saying how for different cloud depths for one liquid water content, and this is different liquid water contents for a lot of different cloud depths. And you notice that the slopes of these curves are all very similar. And another way to show this is to have all these curves and to start off with, pick any one of them you like, and this is giving you nuclear concentration here, number per cubic centimeter. And what we do is we pick any point and then double the concentration, moving over to the right here, and then going back to the same curve, and then doubling it again and going back to the same curve, doubling it again and going back to the same curve. You see that these vertical steps are all really very similar. So this is telling us that the cloud depth and the liquid water content don't matter nearly as much as the initial concentration of condensation nuclei. So another lovely way, this is due to Schwartz and Plinko of seeing this, is to have an axis here, which is the fraction you're going to multiply the initial condensation nuclei by here. So that will be doubling it. What you do is you go vertically upwards from your doubling, and then you go to the left, or you go to this line, sorry, hit the slopey line and then go to the left, and that'll tell you how much you're changing the reflectivity of a cloud drop. And if you were to go to the right, it would tell you what would be right at the top of the atmosphere. So the one number to remember is that if you double the number of condensation nuclei, you get an increase of reflectivity a bit over 0.05. And that saves you doing all the difficult algebra earlier. Next thing is a map of salt being thrown up now before we do any of this lot here. This is gigatons vertically, and here I've got the dates at which the measurement was made. I think it's a jolly difficult thing to measure, but you can see this little big spread and a bit of a trend going to higher amounts of salt. And the average is shown here. And if we wanted to put 1,000 spray vessels working flat out, we would need to have 0.03 gigatons a year. So there's a tremendous reduction from what's actually being thrown up now by breaking waves. And what we're doing is choosing exactly the right size to get the effect that we want to get. It's not the mass of salt. And if you look look at the very bottom of that graph, you can see a very slight thickening of line. I did try to plot 0.03 on there. Okay, now I've lost, here we are. Right, this is another interesting experiment. We've got a set of bars here. There's 20 of them, so there's a 5% difference in albedo between each bar. You can measure your threshold of contrast detection by seeing how many bars you need to see there's a gradient. And if you wanted to get rid of all the heat that's been building up in the oceans, which is the biggest heat problem we face, you'd need to, and we could only treat 15% of the ocean area by doing this trick. The question is, how big a contrast change would you want? And the answer is 2.15%. So about half a bar of contrast change would solve our problem of rising sea level. Okay. Now, this is an interesting thing. It's showing you the solar energy coming in as a function of latitude. That's the south pole at the bottom, north pole at the top. And we've got the season of the year. Right, so it's a big surprise to see that in December, there's more heat going into the South Pole than there is into the equator. The reason is it's coming in over 24 hours. Okay, that means that we do want to be able to move around, not quite going to the South Pole, but we want to have our things migrating. This is showing the patterns of cloud for one instant back in 2008. And here is all the Januaries and all the dunes of 2008 together. You can see where the clouds are. There's some cloud in a lot of places, but there are variations. Somebody recently did a paper showing that you don't actually need to have clouds for this to work. I'm not sure it's going to be replicated. We knew that it's the number of nuclei that matters a lot, and these maps show you lots of areas of the dark blue where it's maybe 10, 20, 30 per cubic centimeter, and other places where it's over 100. But again, they are different, which again says we need to move. And it's the same information month by month for lots of different ocean regions. And here is, for assumptions on the right, how much cooling power you get for how much spray. And the first bit's easier. It gets harder and harder as you have to do more. And this is another one showing you the importance of the movement. The red and yellow bits are really great places, and you can see that you do want to move around through the year. And this is another interesting result from Norway, where they just sprayed where there were clouds. They didn't waste time when there weren't any clouds. And you can see we're getting a very nice increase in the cooling rate up in the Arctic. We're getting 4 degrees of cooling. And all they were doing here was increasing the number of nuclei by 50% in the places where there were clouds. And that's a rather gentle treatment. We could do quite a lot more if we have to. Well, we've got to move. We've got to do we don't need energy to make the spray. And we want to do it anywhere in the Earth. So this says we want to have sailing vessels. And this picture is the ultimate technology of sailing ships. It's Cutty Sark. And they just got this built in time for steamships to come along. And this is a very interesting picture, I think, by Prandtl, the great fluid dynamicist, of a sailing boat with these sails here. But the propulsion is coming as well, or instead of, by these the spinning rotors, these things that look a bit like chimneys with a disc on the top. And a chap called Flettner invented this to rival sails. He got 2 ships, identical sister ships, and he converted one to rotors and had a race against the other one from the Baltic, and he came to Edinburgh. And the rotor ship won the race, and then she sailed across to New York, and everyone thought this was a great idea, and they orders for more, just in time for the 1929 depression. And this is one of the early designs that we had, using Flettner rotors, dragging a big big propellers through the water, much bigger than you need for propellers. These are turbines to generate energy. And we were going to squirt the spray out from fans inside the rotors driven by the spinning. It turned out that the drag from these propellers was going to be much too much. And so we changed over to another system where we've got hydrofoils, and the hydrofoils have got variable pitch, and we can make one foil increase its pitch to try and lift up, and this one reduce the pitch to push down and do the opposite at the stern end. So this produces forces to generate energy for making the spray, which are more or less at right angles, not quite exactly right angles to the direction of flow. So there's much less drag on the boat. When I first drew these, people thought it was ridiculous to go to hydrofoils, but now all the America's Cup boats use hydrofoils, and there's also around the world single-handed race going on now, and about half of them have got hydrofoils. So it's not quite as ridiculous as it first started. That's showing the flapping motion of the hydrofoils, and this is an amazing boat called a moth, and if you get the handout, it'll give you this website. I strongly advise you to download and see how amazing these boats go. I just feel I wish I'd been young enough to fly them. It's controlled by a little stick coming down from the bow, and the angle of that stick changes the angle of the tail foil. Look how tiny these are. Anyone who used to look at airplanes thinks that it's ridiculous to have something flying on the wing that's as small as that. So I strongly urge you to do that downloading. And this is showing you the design of the present vessel. It's got a whole lot of sockets in the hull, and all the equipment for making the spray and filtering the seawater and stuff is built into canisters that are put into sockets. It's a bit like 1960s mainframe computers, where you can just change the card instead of trying to find out a particular chip going wrong. This is really quite well advanced, down to knowing how many fasteners and what seals and bearings you have. I think I will probably be changing the fuselage body, but all the insides are pretty well sorted now. And it would look a bit like this. We've gone away from the original idea with spray in the middle of the rotor. We found there was not really enough room for it, and it obstructed the flow. We wanted a clean flow path, so we moved the spray generation wafers to a mizzenmast, and that has to be able to rotate, so this is always pointing downwind. When the spray comes out, it evaporates very fast. That cools all the air around it, so it actually comes down, not going up. It comes down, it gets the water. The air can't get into the water, so the drops that are entrained in the air can't get in there either. It spreads out over the sea surface, warms up again, and then gets moved up by the turbulence through the boundary lever. So it'll take an hour or so to get up to where the clouds are. This is a rather wild idea to try and get an everywhere to everywhere transfer function of this process. What I'm doing is perturbing a real record of temperature over 20 years by increasing and reducing it in random sequences, which are all different in different places, and then trying to find out what the sizes of the changes were, only knowing what the sequences were. And this is what happens if you put 16 different changes of different amplitudes into a real record. And this is trying to work out, showing the results of a change on the right-hand side of 1.2 and a 1 degree and a 0.8 degree. You can see we're getting really quite a small amount of scatter in the estimates. And that'll get less as, I think, the square root of the length of the record you put in. So this is allowing us to find out what different places do to different other places, season by season, all around. Being tested by a chap called Ben Parks, and it worked really quite well. Here's a bunch of random sequences, all different. And this is showing what the different regions of the world do to one particular place which has got black. And you will see that the code here is that red makes it more precipitation and blue makes it less. And this was confirming an early result from the Hadley Center about marine cloud brightening. Actually, people were very worried that this would dry out the Amazon, but in fact, most places will give you a slight increase in the Amazon. And to our surprise, this place down here is going to get more precipitation if you go and spray off the Aleutian Islands. There's many a PhD lurking in there. Now, here's another way we can use it. The Indian Ocean dipole is the temperature difference between Africa and Australia. And if you have it cooler on the Australian side, you get less rain in Australia and more rain in Africa. And this has been happening recently. And what we would like to do would be to adjust the temperature difference by moving fleets of spray vessels east or west to get a balance that's more comfortable for people to not have excess flooding in Africa or bushfires in Australia. And we need to get the Australians and people in Africa to agree what was a happy medium. And this is what we would try to avoid. This is the kind of thing that's happening recently in Kenya, and this is what was happening last year. It's just starting up again in Australia. The next thing we might be able to do, this is from Whitney and Hodgood, showing the severity of the intensity of hurricanes against the sea surface temperature. Warm seas are a necessary, not sufficient condition for getting a hurricane, but you can see that they really do drive the severity. And no one's going to be brave enough to say, we promise you'll never have another Category 5 hurricane. But what we could do is to get the governments around the Gulf of Mexico to agree on a pattern of sea surface temperatures, which they think would give them gentle hurricanes, maybe tropical storms, or maybe a Category 1 or 2. They do want the water, but they don't want Category 5. And what we would, this is, by the way, the paths of all a whole bunch of hurricanes. They start over on the African side, and they get more intense as they go towards the west, and then they curl around, and some of them end up coming to Europe. And the same thing happening with the Philippines here. And what we would want to do would be to have, this is a recent thing, see these chaps standing on the roof. What we'd want to do would be to have fleets of spray vessels moving around from Africa towards the Gulf of Mexico, tracking the sea surface temperature. You start doing this in November, and you keep looking at the sea surface temperatures, and you'd adjust the number of boats here to try and get the trajectory of temperature rise to balance what the governments in the Gulf decided was okay. And you pay the sprayers according to how close they'd get to the nice target, the moderate rainfall and not too dreadful winds. We'd have to get them to agree, and that may not be very easy, but I think they would like to be a reduction. This is an experiment which is trying to find out how you could measure the performance of spray ships with a very small quantity. What I got down here is a whole set of conditions which are spray vessels probably do about 30 kilograms a second. So this is just doing a 10 kilogram spray source. This is the wind speed, how long it's going to take up to get to the clouds, how fast they decay, how deep the boundary layer is, and the initial concentrations. All these are really quite severe. And I'm producing maps here of the number of pixels would be per cubic centimeter, widening out from the spray source. I don't know what the angle is, so I've got 4 angles. And there's a decaying of the concentration as well. What I do is I put this diagram here into the Twomey equations to get the brightness patterns of clouds here. This is South America, and each of these pixels has had the Twomey equations applied to it. And if you look down here, you'd have to be extremely convincing to persuade anyone that they wanted to invest in this project. All right. And however, if you take 100 satellite images, you can see these wakes emerging from the mist because we're averaging out all the different cloud positions. That's 100 satellite images given to me by Rob Wood from the University of Washington. And this was a big help. It means we can find out what's happening in lots of different places and lots of different atmospheric conditions, so that we can really decide whether it's worth trying to do bigger spray amounts. This is performance for different missions that we might want to take. We might want to get rid of El Nino events, so we might want to cancel hurricanes, save the Arctic ice, cool the barrier reef, and push down sea levels. And these are the amount of water we need to cool. Here we're trying to cool the entire sea. 350 times 10 to the 21 joules we've got to get rid of. In 20 years we're allowed to do this. And this is telling you how many spray vessels you'd need to do this if they were all working in the right place at the right time. They might not be able to do that all the time, so you might want to double that number, but it's not a ridiculously large number. We think that, well, if we can index link the cost of ships that are made in similar numbers, most ships are made in very 1s, 2s, and 3s. An exception is the Flower class corvettes that were built in 1940. And if you can index link their cost, which was £60,000, spray vessels would be costing about 3 million each if you're making them in that sort of number. So this will tell you how much you need to borrow from the banker to do these different jobs here. And when you work that out, it looks as though it's going to be cheaper than having the conferences. I wanted to finish by reminding you of this wonderful result here from Norway. It's doing fairly even cooling, even though the clouds are not continuous, a lot more in the Arctic. And if you look at the precipitation, which was the worry, you can see that the blue-greeny bits, which is where we're increasing precipitation, are where the deserts are and where they'd be glad a little bit. Now, this is a percentage increase, and if you've got a very low amount to start with, a 10% increase isn't all that exciting, but we are getting up to 20% increases in places that we really would be quite glad of it. The places where the technology is going to be reducing precipitation are all over the sea, okay? Or they're at high latitudes where people aren't nearly so worried about not getting enough rain. But these really heavy ones are over the sea. There may be small islands in the sea which would be suffering here, and we'd have to find a way to pay for desalination. I really would like you to take this pair of images away. That's why I'm reminding you. And I hope now you have enough information to decide whether this gentleman was right or whether it was me. So now I will try to answer any questions. Does someone?
Thank you very much, Stephen. That was really fascinating, and I'm sure it's one that a talk that is going to spark a lot of debate. We have had a number of questions so far, but just before we start on the questions, there was one from Tracy about copy of the slides. Tracy, if you're still there, can I suggest that you probably best to email RMetS, who can pass that request on to Stephen. There may be some copyright issues with the slides, but I'm sure Stephen will be happy to address that one directly to you.
Or you can send them directly to me. My email address is on the handout. I've acknowledged all the sources where I know them. And if I haven't got a source there, it's me refused.
Okay, right. Our first question from Nigel. Perhaps, Vicky, you could put these up on the screen as well, please, so we can see them. But the question was, what area globally is required to brighten the clouds to have an effect on reducing global warming?
At any one time, there's a terrible echo, which is, I'm going to turn my sound down. I have to turn it up again because my sound's going off. We think we want to do it where there's sunshine and clean air, and where there's a moderate size of wind. I think we can do it almost anywhere, and the map by Oriopolis is probably the best single guide at the moment. But the places we wouldn't want to do it would be where you've got heavy pollution being blown up, maybe from China or the east coast of America. But otherwise, you can do it anywhere. And remember, we only needed 15% of the oceans to solve the sea level rise in over 20 years. So the answer is, the people who are controlling the fleets will have calendars to say what the time of year is, and they'll also have satellite data, and they'll be deciding where to move and where to stop spraying to get the results that they were clever enough to decide is what everyone wants. So I think the answer is almost anywhere except where the air is already very dirty. Right, my sound is back on now. Another question?
Thank you very much, Stephen, for your answer. The next question comes from Andy. Can CCN be seen as a key contributor to possible global dimming, or are other aerosols equally as important?
There will be dimming, but it'll be mainly over the sea. So it's not going to be affecting crop growth. The places in the sea, I have to turn my sound down. Places over the sea where you get a lot of chlorophyll are places where the phytoplankton are already doing the job. So we wouldn't need to go particularly where the phytoplankton are producing the beginning of the marine food chain. In fact, it may be possible that we could give the phytoplankton a help by increasing the amount of iron in the sea, and so we could maybe make other places also produce the start of the food chain. My microphone coming back up again. Hello?
Thank you again, Stephen. We have a bit of a political question from David. Is there a danger that, like with the imminent coronavirus vaccine, people relax and put off the real long-term solutions?
It's possible. I think having too many solutions is better than having too few. But that's human nature. I think we have to get every single possible viable cooling technology at least tested so that it's ready. If people can get carbon dioxide emissions down quickly, and there's no evidence at all that we can, then I'd be very happy if all the spray vessels were just parked and maintained. It's been like having armed forces that are trained and equipped, but not having a war. I think that's the right way to do it.
Less political one, more technical from Sylvia. Looking to query the precipitation change map. Is a negative change not a reduction in precipitation?
I didn't hear that because of the echo.
Oh, sorry. It should actually be up on the screen there for you to read. There is a bit of echo in the background. And sorry, people who are out there listening, apologies, we do have a bit of an issue with sound tonight. I'll just read it again, in case you can't see it, Stephen. Sylvie would like to query the precipitation change map. Is a negative change not a reduction in precipitation?
Let me try and go back. The greeny blue bits here are increasing I think I may have got my things the wrong way around. Oh dear. I certainly mean this is, the greeny blue bits are meant to be more, not less, and I've got my minus signs the wrong way. Oh God, what a stupid thing to do. Yes, we will be making more rain in the greeny blue bits, and I've screwed up.
Okay, I think we'll just leave that one there then. Sorry about that one. Right, one from Shona, and she says, good to hear something positive near the pole. Sorry, near the pole, if you make the cloud droplets smaller, have you checked that the decrease in snowfall over the ice is less than the decrease in melt from the cooling? Also, how would the change surf salinity and temperature affect the sea ice, and therefore the relativity and local ocean circulation?
I really don't know enough to be able to answer that, but turn my sound, my micro off. My calculations are that we would start off by saying what's the mass of the sea ice that is going missing, and if we multiply that by the latent heat of ice, that'll tell you how many joules are have to be got rid of. And if we know what the sunshine input is, we'll know how much we got to increase the reflectivity to offset that number of joules. Now, I don't know enough about rainfall and icefall and snowfall, but I know that the reflectivities of snow and ice are really quite similar. And both of them are very much higher than open water. So it wouldn't matter whether there was snow on top of ice or ice without any snow on top, we'd still be doing a good job. We'd have to do it just for a month either side of midsummer. And there'll be ice and snow blowing around. I think that the reflectivity of snow falls after as it ages, and it goes down towards being icy. But that's cloud physics way above my pay grade.
Another one, sorry, Stephen, another one from David Stevenson. Do you think the cloud physics scheme in climate weather models are sufficiently well understood to really know what spaceships will do? Models currently struggle to simulate distribution and trends in clouds and the precipitation. So do we really know what adding extra sea salt aerosols will do?
No, we don't. We need to do a lot more. I hope with quite a small spray source going in lots of different regions, lots of different weather climate conditions. I think the ideal thing would be to have a zigzag course going from Peru down to the Antarctic, then back up to the equator and down again and back up again, all the way across to New Zealand. And I think if you did that over at least 6 months, then you might be able to get the answer to the question. But at the moment, I am not impressed by the amount of knowledge we have about clouds and physics. I'm just making the best use we have, and I hope that we can get lots more proper, sensible cloud modeling done. Maybe starting off with some experiments to take actual measurements. When I started on wave energy way back, I was completely ignorant about waves, and I was amazed at how much was known, but also by how helpful all the people who knew it were to help us get going. And it's exactly the opposite with this. I'm surprised at how little we know and how hostile people are when I ask them questions that they can't answer. So I'd like to get back to the help we used to get in waves. Is that David Stevenson, the David Stevenson that I know? I do know a David Stevenson who's in this business, and I've tried to get him to help. Is that you, David?
As well, so I suspect it is.
Probably is him. Yeah. We need you.
Okay, thank you for that one, David. Martin, one question from Martin, next question. What size number of vessels would be required to generate a useful test? For example, what would be the useful demonstration and allow us to measure an effect?
I would say one. We'd get an awful lot from the very first one if we use it in lots of different conditions. And we will only have one to begin with. Did you get that? Everything's gone quiet.
For that, I think having my microphone is creating a bit of feedback with you, Stephen. So a question from Helen, who said it's a slightly odd question. If eventually deployed, who would own and be responsible for the security of these? Would they be at risk from hijack or hacking?
They would be vulnerable. They can actually go quite fast if they're not spraying. And if you've got hundreds of them all around the oceans, they can also report all the suspicious looking vessels. So the net value against hijacking might be positive. You've got real TVs almost everywhere, and you can see what you're suspicious about. So this plus a few drones, I think we could deal with the hijacking problem. If you really did want to get rid of them, you only need to take a hacksaw. If someone knows how to run a fishing boat and can carry a hacksaw, if you can get aboard, you would be able to demolish them. So they're not in the same category as robot soldiers. We're going to have to deal with the piracy problem, or whether we have a climate problem or not. The minimum drag is when they're going at 9 meters a second, which is about 18 knots. So if we stop spraying, we really can go quite fast, and we can have clever communications with the security people. Okay, thank you, Stephen. We have a question, another slightly political question from Erin. The IPCC report talked about the risk of a termination shock if mechanisms of solar radiation modification are abruptly stopped. Though there's some debate over how serious it would be, is it ethical to take that risk? Starting something we can't necessarily stop quickly if we don't like the effects in practice. I think it would be ethical. I must turn my microphone off. It would be very unethical to have something that you couldn't reverse. Let's say that there's another ice age starting. We would want to stop this spraying very, very quickly. The termination problem is if you did turn them off, it would take about 10 years to get back to where you would have been if you hadn't ever started. And that's about a comfortable time to do the repairs. If you've got a few hundred spray vessels and suddenly there was a major problem and you have to replace them, you could do that within the 10 years. But I wouldn't want to have something which was never going to be reversible. I think it's an unnecessary concern. You should be able to choose the amount of cooling you want and going back down to zero if you decide that's a good thing. But 10 years is a long time to fix a fleet of cars. It's like saying, what would happen if all the buses suddenly broke down? Some buses do break down, but not all at the same time.
Thank you, Stephen. I think that was a really good answer to that question, actually. That it just shows the vulnerability of everything, not just this particular topic. A question from Leslie. Now, her question is one that I would have asked, but in a slightly different way. Is when is the vessel likely to sail? In effect, I think what she's trying to say, and the question I would have asked is, when will this actually become reality? When could we possibly see the first vessel actually out on the ocean doing this.
Right. If we had quite a moderate amount of money, I think it would be 5 years. That would be a sensible time. If you want to do it more quickly than that, you'd be doing lots of things in parallel, and not all of them would be used. But 5 years would be a sensible time. And I've got a plan worked out for what we need to do for each of those. There is a number of showstoppers that could show we can't actually do it after all, and we would know about those in about 1 year.
I think that's all the questions that we have, and I think it's been a very full session. And Stephen, I would like to thank you on behalf of the members of the Scottish Centre Committee. It's been a very full talk and a very engaging talk. We've had more people listening in tonight. I think it peaked at 85 than we've ever had before. So it's obviously a very emotive subject, and we're very grateful that you took the time out to give us this talk tonight, and we wish you all the best with this adventure, and we look forward to seeing something positive coming and actually happening. 5 years is not a long time. For some people it's too long when it comes to climate change, but I'm sure we will see something, and we hope that you can keep up the good work. So thank you very much, and I'm sure if everyone could applaud, you would hear them, because it was really outstanding tonight, and thank you very much. Those that are still there, I would like to just remind you, please, about our next meeting, which is by Dr. Matthew Eyre of the University of Calgary. This is the great thing about these videos, rather than the video chats or conferences, rather than being in a lecture theatre, that people can join from all over the world. And I did see that we had somebody as far as Italy tonight, which was really nice to see that it's not just Scotland. We're seeing people from all over the world coming on. The talk that Dr. Matthew Eyre will be talking about is recovering observations from a whaling wreck in Baffin Bay. Now, this is one I've actually heard him speak on before, and I would thoroughly recommend it. If you log on to the RMetS website, you can actually register for this now. So I would look forward to seeing you all again next month. And I would again thank Professor Leslie Salter for his talk tonight. And I would wish you all a very happy Christmas and New Year. I look forward to seeing you all in January. Thank you very much. Thank you.